Hi everyone, my name is Vaibhavi. I'm from Carnegie Mellon University. Today in this video, I'm going to talk about my attempt to build a predictive model for intrusion detection, and the dataset that I'm going to use is KDD Cup 1999 dataset. So let me begin by telling you what intrusion detection exactly means. Whenever a machine receives a connection request, it is not necessarily a good connection request. It might be an attempt of a network attack on your machine. So your intrusion detection system should monitor your network in real time, and it should be able to identify such attack attempts. It should take corrective steps so as to not let your machine get harmed by those attacks. It should also store the event information or information about these attacks so that in future you can use this information and you can classify or identify new attacks. The task is that I have to build a predictive model which will be able to distinguish between good and bad network connections, and I have to further classify the bad network connections into the categories of attacks. Data that I'm using has a training data set and a test data set. The records in the test data set are basically records that I don't know about. That is, the records in the test data set, I will classify those based on the information that I get in the training data set. Training data set is about 4 GB of compressed TCP dump data, and test data has about 2 million connection records. And every record in both these data sets is about 100 bytes. In the training data set, there are about 24 attack types, and all these attack types can be grouped into four main categories of attacks, which are DOS, R2L, U2R, and surveillance or probing. In the test data set, there are 14 additional types of attacks, 14 additional which are not present in the training. So, how do I identify these attacks which are not present in the training data set? Um, well, every new attack is normally a variant of a past attack. So, if you have a signature of the past attack, you can easily identify the new attack types. So that's what we are going to try to do. Every record in both the data sets, it has about 41 features. These features can be grouped into three categories. First is basic TCP features, which are features like duration, protocol type, or service. Content features, which are features like whether the user is logged in, how many failed logins has the user had. Next is traffic features, features like, error rate. Okay, now what did I try with the data sets that I had? I firstly used the 10% training data set, and then I went on to using the full training data set. I used the corrected or labeled test data set because only then I could identify the accuracy of my model. The classifiers that I used were KNN, knife Bayes, and decision trees. I first ran knife Bayes on the 10% training data, and I got relatively poor accuracy. This is the R code snippet for knife Bayes model, and these are the confusion matrices. To summarize, I could only identify 191891 records correctly with knife Bayes model, which is about 61.69% accurate. One important observation here is that it only identified 342 out of 60593 normal records correctly. This is because in the data there are more bad records than there are good records, and knife Bayes is a probabilistic model, so it is biased. Next, I tried to run KNN on the data set. This data set is a mix of both factors and the numeric features. So to run KNN successfully, I had to convert the factors into the numerics except for the last one. Um, then I then I tried to run decision tree on the 10% training data set. These are the confusion matrices and the R code snippet for decision trees. With this, I could identify 248947 records correctly or classify them correctly, which was about 80% accurate. And one important observation here is that the data that was misclassified was classified as normal. Okay, now let's think about what are the problems with the data set. What problems can we overcome, which can lead us to getting better accuracy or better accurate results. So the first is that redundancy. The data set has a lot of duplicate records. And next is not all of the 41 features are relevant. So next, I tried to deal with the redundancy factor. I tried to run the KNN model on the unique data set, unique as in removing all the duplicate records. With this, I got about 91.7% accuracy, which was really good. I could identify 285231 records correctly. I tried KNN for different values of Ks, but I got the highest accuracy for K equal to 5. I tried running decision tree for the unique training data, but I actually got decreased accuracy. My accuracy was decreased by 50%. Knife base did comparatively better with the unique data set. Its accuracy this time was 72.35% as opposed to 61% last time. It also identified more normal records correctly. Then I thought of distinguishing between good and bad connections instead of directly classifying connections into the attack types. So I converted all non-normal records as bad, and I used decision tree with this new data, and I got 93% accuracy, which is really good. Next, I tried identifying good and bad connections using unique training data, but my accuracy actually decreased a little. I got 90% accuracy here as opposed to 93 last time. After successfully classifying data into good and bad, I tried to classify the bad connections further into the 4 attack categories. So then I labeled the respective subcategories of attacks to uh, the grouped category. This is the R code for that. And then I use decision tree to classify the data into these 4 attack types. And on overall data set, I got 91.7% accuracy. DOS, I got 99.85% accuracy. I classify normal records with 99.66% accuracy and probe with 77.66. It couldn't identify any of the R2L or U2R records correctly. These are the confusion matrices. Okay, now next problem was that not all the features were relevant. So we have to do some feature engineering. We can apply domain knowledge. For example, if it's a DOS attack, we know that the protocol type is probably going to be ICMP. So we can use this domain knowledge and derive some rules or signatures, or we can use relevant features for particular data or particular types of attacks and use those to train our models to get better accuracy. For example, for normal type 1, 6, 12, 15 are the relevant features. So train your model with these features and you'll get better accuracy as far as classifying normal data is concerned. In R, there is a method called VARIMP, which actually gives you the features that are most important for your model. So I tried it for my decision tree model and I got V2, 23, 24, etc. as the most important features for my model. And I used these and I tried running my decision tree with these relevant features, and my accuracy actually increased from 80% to 82.93. And one more observation about the data set is that in the test data set, 90% of the records belong to either normal, Neptune, or Smurf type. So if you could use the relevant features to these 3 types, we will get about 90% of the accuracy. So out of the 3 models I used, Knife Base gave me the lowest accuracy. It is probabilistic model and so it is biased. KNN is better for continuous values since this data set is a mixture of both factors and numericals. Decision tree worked best. Also with decision tree, we can also do feature engineering. We can select relevant features and train our model accordingly. We can't do that with any of the other models here. So my best feature model combination was decision tree that I used to classify data into 4 attack types, and the decision tree where I used relevant features and trained my model. I got better accuracy in these two cases. Now, what future work can we do to get better accuracy and better classify the data? First is that instead of using a single algorithm, we can use different algorithms, or in single algorithm, we can use relevant features particular to different attack types. Next is we can derive some rules or signatures based on the domain knowledge or relevant features, and we can use these signatures to identify or classify our test data. So that's about my experiment. Thank you.